Okay, so now that we've learned about the layers of the atmosphere, I want to zero in on the stratosphere and talk about stratospheric ozone and the depletion of stratospheric ozone. Okay, so the sun gives off light in a broad spectrum of wavelengths, everywhere from very low energy infrared light to high energy X rays. Now, most of it is produced in this region here, which is visible, which our eyes can detect. We have little antennas in our retinas that can pick up these signals. But the ultraviolet light is above that. And so the sun does give off a bit of light in that ultraviolet part of the spectrum. We just call it UV for short. Now, we can take this UV part of the spectrum and divide it into three categories, largely based on how they interact with organic material. So, UVA is the lowest energy of all the UVs, and it is less energetic and less harmful. UVB is more energetic and it's more harmful. This is what gives us skin cancer. And then there's UVC, and there's not a whole lot of UVC reaching the ground, for pretty much none, but it's the most energetic and the most damaging to cellular tissues. Let's just talk a little bit about UVA and UVB because that's what reaches the Earth. So, UVA light, it's too short of wavelengths for your eyes to take. You don't see it, but you can sometimes feel it. It's basically it penetrates your skin and it causes the production of melanin, and that's what gives you a tan. So a tan itself is not necessarily an indication that you've put yourself at risk for skin cancer. That's just UVB light, but unfortunately, UVA light rather. Uh, but UVB light is more energetic, and when it hits your skin, it has a tendency to ionize molecules, turn them into things called free radicals. And these free radicals then damage DNA. And when you damage DNA and it goes to repair itself, that's when you get these mistranscriptions that then eventually lead to cancer. The reason I'm not here today is because of skin cancer. Don't worry, it's probably not malignant. It's benign. I've had a number of these in my life, but I got exposed to a lot of ultraviolet B as a kid at the beaches in the Philippines and North Carolina, and my skin is paying a price for it now. So, bottom line, UVB is something we don't want to be exposed to because it does cause cancer, and it doesn't just hurt humans; it hurts plants as well. Now, it could be a lot worse. There's a lot of UVB that comes from the sun, but most of it doesn't reach the ground, and that's because of stratospheric ozone. So let's talk about how stratospheric ozone is formed. I talked about this in our last one. Let's just go ahead and review this. In the atmosphere, in the stratosphere, we have O2. That's diatomic oxygen. Is the main kind of oxygen. When UVC, the most energetic form of ultraviolet light, is hit, when it hits oxygen, it gets absorbed, making the stratosphere warm, and breaking apart into two monatomic oxygen atoms, which are highly reactive. These will eventually encounter one of these, forming one of these, O3. So when I split this, I end up making two of these. These O3 molecules are called ozone, and ozone is a fairly delicate molecule. That last oxygen is not hooked on nearly as strong as the first two were. So this conversion of O2 into O3 by UVC light tends to occur in the stratosphere between the level of maybe say 10 and 50 kilometers above us. Now, let's talk about what happens with UVA light. UVA light, which is the kind that causes tanning but not cancer, it passes right through nitrogen, right through O2 oxygen, and right through O3 ozone. Passes right through it, comes to the ground. Basically, the stratosphere doesn't block it. But it's a very different story when it comes to UVB light, fortunately. So what happens is UVB light can pass through regular oxygen, just like UVA can. But look what happens when it hits an ozone. When it hits O3, that UVB light hits here. I made it violet because it's ultraviolet. Pretty cool, huh? All right. When it hits this, the energy goes into breaking off that extra oxygen that was a monatomic oxygen that got stuck on it. It breaks it off of there. Now that used up this energy, so it doesn't make it to the ground. So that ray of a photon of UVB light that was going to maybe give you cancer, thank goodness its energy got expended, breaking this oxygen off of O3 and turning it into O2 and a monatomic oxygen. Now remember, monatomic oxygen, it's going to find diatomic oxygen, hook onto it, and form another ozone. So this process is constantly going on, right? O3 gets hit by UV light, breaks apart. Then after it breaks apart, it falls back together. So look at this profile of the atmosphere. UVC light from the sun, it all gets used up in the stratosphere, never makes it even to the bottom of of the stratosphere. It's basically where it gets expended is breaking O2 into O. Ozone then depletes the light stream of UVB light for the most part. Although by the time you reach the bottom of the stratosphere, there's still some of it left, and it does get to the surface. So there's nothing down here to block it. uh, UVA pretty much comes through almost entirely undiminished upon reaching the ground, all right, because it doesn't really interact with anything. So remember, UVA is not really a problem, but UVB is. So UVB, I alluded to cancer, which it causes, but it also causes cataract. So a lot of us, if we live old enough, will have to have the cornea of our eyes removed. I've had this happen to many of my friends, my parents, relatives. Uh, and it can also cause reduced photosynthesis in plants, which impacts all food webs that are reliant upon them. So we don't want to have increases in UVB light hitting the earth because it can impact the entire global ecosystem. Now, ozone depletion, unfortunately, is something that humans have precipitated unknowingly, but this story actually has a happy ending. So there's certain man-made chemicals that we can release that enter the stratosphere and they break apart ozone and turn it back into O2. Now, there's a lot of chemicals to do this. We're just going to focus on one category called CFCs, chlorofluorocarbons. So chlorofluorocarbons, well, what are they used for? Like the most popular one that was ever made was called Freon. So these things are primarily used in refrigerators and air conditioners. You need some kind of chemical that you can compress into a liquid and let boil, and that's what takes the energy out and makes it cold. So they get used a lot in that. They're used in fire extinguishers. They're often very good as propellants, so that's why they're fire extinguishers and they're spray cans. They're also present in insulating foam, sort of spray foams. So that's what CFCs were used for. Notice I use past tense because they're not really used anymore because we realized they were causing a problem, and then we fixed that problem. So here's how it works. This is a typical chlorofluorocarbon called Freon. Now what happens is when UVB light in the stratosphere hits this, it will break off one of these chlorines. Now I just have this atom of chlorine drifting around in the stratosphere, and this right here is a problem. It came from chlorofluorocarbons, but it broke off and formed chlorine. Let's see what it does. So here's chlorine. Here's an O3 ozone. Remember, ozone we like because it blocks UVB light. Here comes chlorine. Chlorine is very reactive, so it grabs hold of this and it breaks this one off, forming a ClO molecule and turning this O3 back into an O2, which does not block UVB light. So this would have blocked it, but now it's gone and I have this, and that's not blocking it. So you can see how that's problematic, all right? But wait, it's a lot worse than that because if it's just one chlorine broke down one ozone, we wouldn't have had a problem. But unfortunately, what happens is this ClO molecule, when it drifts around, if it finds another monatomic oxygen, which remember UVC light takes O2 and turns it into O and O, if it meets up with one of those, which it will, then this joins these two together to form another O2, and chlorine ends up back by itself, which is what it started out as before. So, in this sense, the outcome of this two-step process leaves chlorine back where it started. That's what we call a catalyst. Essentially, when Cl is in the atmosphere because of chlorofluorocarbons, it basically takes O3 and breaks it down into O. And one of these can keep doing this for dozens of years, for decades. One of these can break down millions of ozone molecules. Now, what happened was, as we're going to find out throughout this year, unintended consequences. People thought these are great chemicals because they're non-toxic to humans and other animals. It seems like a great idea, and they're great at refrigerants. They're great at propellants. So when we use them like crazy, and all of a sudden people start noticing, hey, you know what? I'm detecting a lot more ultraviolet light hitting the ground than we used to. And they realized, oh my gosh, here's what happened. We started generating CFCs back in the 50s. And what happened was, as this went up, watch what happened. So by 1987, we finally outlawed them. Man, we were generating so much of them. Now look what happened at the same time period as these were going up, the amount of ozone was coming down, and the amount of UV light hitting the Earth was going up. So people said this is potentially catastrophic. This could cause a collapse of ecosystems, and not forget just cancer for humans. This could be really bad for plants. If you hurt the plants, you've hurt everything. So what people did about it was, this is just showing that basically the basically, what are we looking at here? We're just seeing how much starting in the 60s, we can see how the amount of ultraviolet went up, and this is showing in different latitudes. We're seeing that more of it happened as we got closer to the poles for reasons we don't have to go into. Okay, now here's the other thing I need you to know. It is possible to fix environmental problems. And when you take this course, it might be easy to convince yourself, well, there's something we can do about any of it. It's just depressing. No, it can be done. It just takes people understanding the problem and having the political will to fix it. So here's what happened. When people realized this problem, the countries of the world got together. I'm talking about 190 countries. That's almost every country on the planet. They got together and they signed a thing called the Montreal Protocol, which is happening in Canada. And they basically said, we're not going to make these chemicals anymore. They're very profitable chemicals. They're very useful chemicals, but they're damaging the world. So we're going to stop. We're going to tell our chemical engineers to come up with something different, which they did. All right, HCFCs. But the thing is, they came up with that, and so starting in 1987, the amount of CFCs emissions came way down. You still got some bad players out there that still make it. China, people like that still make it some, right? But we've dramatically reduced the amount of CFCs being produced, courtesy of this one accord, the Montreal Protocol. And look what's happened. So basically, what happened was the amount of ozone in the atmosphere, starting in the 1960s, started dropping down. Now we're going to just look at the Antarctic because that's where it happens the most. Started dropping down, and then around 1986, I think it was 87, we signed the Montreal Protocol. But look, it kept dropping down. Why? Because remember, those chlorine atoms stay in the atmosphere, catalyzing ozone. So it takes decades for them to come out of the atmosphere. But look what happened starting around a little after 2000. Ozone started coming back, and now it's coming back, and we can look at the trajectory and go, look, by the end of this century, we'll be back pretty much to where we were before we started making this. The point is, we can identify these problems, these environmental problems, we can address them, and we can fix them. There is hope. If we did this for ozone, we could do it for carbon dioxide, as we're going to talk about later in the year, which is the big one that your generation is facing. And so when we see this, it gives us hope. It's a little bit more of a tricky one to fix, but it can still be done. So thank you for watching. Sorry, I got off on my soapbox talking about saving the planet, but thank you for watching, and have you do another activity.